In this example, we are going to be talking about velocity and acceleration. We got ourselves a graph, and let's kind of go through this, what the wording is for this. So it says, suppose the position in feet of an object moving horizontally along a line at time t seconds is, so this is the equation that represents its position between 0 and 5, maybe 0 and 5 seconds. This graph on the right is supposed to represent that. Assuming assume positive values of s correspond to a position to the right of s equaling 0. All right, so it says graph the velocity function. So when they talk about velocity function, if you remember real quick, to find a velocity, that means we're going to be taking the derivative of the position function. All right, so that's one thing we're going to do. And we're going to graph that velocity function from 0 to 5 and determine when the object is stationary, moving left, and moving right. Here's where the signs are going to matter. So let's start with, let's find our velocity function, which is basically us doing the derivative of that, right, which is velocity. All right, so when we do this derivative, we're going to take the derivative of t squared, which is 2t minus 5, and that's it. That's our velocity equation. So what does that look like? That looks like from 0 to 5. Let's focus on 0 to 5. 1, 2, 3, 4, 5. And this would have a y-intercept at 1, 2, 3, 4, 5. And then we'd be going up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Okay, so each of those points would be representing velocity. All right, so that's an important thing. They're not positions, they're not y values, they're not distances, they're slopes, they're rates of change. Okay, so we have negative slopes, we have positive slopes, and this is a slope of 0. So that is exactly what they're asking for, is determine when the object is stationary. It's stationary when its velocity is 0, moving to the left when you have negative slopes, and moving to the right when you have positive slopes. So it's stationary when when this equation, and we have the visual, but let's say we do the math on it and we don't have to create a visual to it, is basically when you take your velocity equation and you set it equal to 0. And so if you add 5, 2t equals 5, we would divide by 2, t is going to equal 2.5. So at 2.5 seconds, your object would be stationary. All right, so when is it left? Moving to the left. Left is when our velocity, or derivative, is less than 0. So we do the exact same math. We're going to take 2t minus 5. It's going to be less than 0. And if we do this math, we're going to add 5 over. So 2t is going to be less than 5. Divide by 2. We're going to have t is less than 5 halves, which means t is less than 2 1/2. So when is it moving to the left? When we are less than. So really, we're talking about from 0 to 2.5. We would be including 0. We would not be including 2.5 because at 2.5 it stopped. Right, and you can kind of see that happening here because this is all about the slopes right here. Right, so we have these negative slopes that are happening. You have these negative velocities, so it's heading to the left. And then at 2.5, it stops. Right, but even at 0, it was heading to the left. It had a negative slope instantaneously. And then it starts to move to the right. And so then the right is when our slope is greater than 0. So we would do this exact same math. The only difference would be instead of it being less than, it'd be greater than. So our time would be when we are greater than 2.5, but it doesn't go forever because we're really only going from 0 to 5. So our position, our moving right would be from 2.5, right, not including it, to 5. And at 5, we would have a positive slope. You could see it here, and you could plug in 5 into this, which would be 10 minus 5. So at that instance that it ended, it still had a positive slope on it, right? So it was still moving to the right. So this is really how we should be representing our answers. And then we got 2 more. It says graph the acceleration function. All right, well, the acceleration function is, go back over here. Acceleration is the derivative of the velocity, or the second derivative of your position. Okay, so our velocity equation, our original equation, it was t squared minus 5. Our first derivative was 2t, so that should be minus 5t, was minus 5. And then our second derivative, which is our acceleration, is just 2. So graphically, from 0 to 5, we are at a height of 2. So our acceleration, that all that means is that our acceleration is just constant, right? That's the biggest thing to it. So constant positive acceleration. All right. And then the last thing, it says describe the motion of the object. So we initially had, if you look at your slopes, we initially had our object was moving left from 0 to 2.5, and then it stopped. And then from 2.5 to 5, it was moving right. And so that's kind of what our slopes are describing it as. So the object moved left with decreasing speed. Okay, if you really look at the graph, so we're kind of getting specific because your positive acceleration is slowing negative velocity down. So you have these slopes that are constantly getting smaller and smaller and smaller. They are negative, but they're decreasing. And that's because positive acceleration is causing negative velocity to stop. And that's exactly what happens. And so we have decreasing speed. It was moving left until it stopped at t equals 2.5 seconds. It then began moving to the right with increasing speed. And again, that has to do with the fact that you have, when you start moving to the right, we had positive velocity. And then not only did we have positive velocity, but we had positive acceleration, right? Positive acceleration with positive velocity means you're going to be picking up speed. So that lines everything all up, agrees with our graph, all hopefully makes some sense.